Alright, hello everyone. My name is Glen Wheeler. I'm from the University of Wollongong in Australia, and you might ask, who? And of course, I can help you. I'm here to help, and I can write my name at least. After too many years of education, at least I can write my name. Here it is, Glen Wheeler. And what was that university? Has a funny name, right? Well, it's just UOW, or University of, and then this letter is standing for Wollongong. It's an indigenous word, meeting place, and it's a good word. I like it a lot. And where the bloody hell is it, eh? Well, whenever I want to find something, I ask Google for help. So here we go. There's Australia. So if you are somewhere else in the world, hopefully you can manage your way to the great southern land. And then we can zoom in. Now I've got a little flag where there's a nice cafe, just in case you were wondering what that flag is. And here we go. So just south of Sydney, we've got Wollongong. And we just zoom in a little bit. And yeah, you can see there's a nice little few beaches here. There's a golf club, some music centre, and then over here, if I can find it, yes, the uni bar. Haven't been there in a while. It's a bit difficult with the lockdown, but looking forward to it. And there's the University of Wollongong. Okay. You might think, what does it look like? I can help you, again, with the power of Google. I googled Wollongong in the image search, and there's some nice pictures. And I might click university because that might be more relevant. There's a nice new building, some fancy photography. Yeah, there's the campus. I like this one. And there's the logo. Okay, enough. Alright, so what do? I do mathematics, and I'm going to talk to you about a curvature flow problem. I'm mostly interested in curvature flow, like geometric heat equations, geometric evolution equations, normally higher order equations, but also second order from time to time. And this time I would like to talk to you about two geometric evolution equations supported on parallel lines. Okay, so here you have parallel lines, and this blue curve, it's just a curve problem. I'm just going to talk about curves this time. Maybe later we can do other things. Okay, and what are my two evolution equations? The first one is the so-called curved diffusion flow, like this. The curved diffusion flow is, in a sense, the h-1 gradient flow for length, and it has evolution equation like this. It's a normal Laplacian of the curvature vector. So it's like a biharmonic, it's a kind of biharmonic heat equation. You can think of it like that. It's not exactly the biharmonic heat equation, but it's like that. And the other one is the free elastic flow. Okay, this one is the L2 ds steepest descent gradient flow for Euler's elastic energy without any constraint. So no length constraint or length penalization term, and it has velocity like this. Okay, so here I've just used the Greek letter nu to mean normal vector, and this k is the curvature scalar. This subscript is the arc length derivative. And to these equations I supplement some boundary conditions. Maybe I shouldn't write in red. I don't want to be too aggressive. So it's got free boundary on these parallel lines. There's a Neumann condition, so we just make it 90 degrees. on the lines. And no flux. No flux condition is that the derivative of the curvature scalar on the endpoints is equal to 0. Okay. And also I should say that this thing that I'm going to talk about is joint with the wonderful Valentina. So I'm trying to figure out where I can write her name. I'll put it in pink because pink is the greatest color. And so this is joint with Valentina. Okay, now I'm aware that my time is quickly running out and I haven't even started my actual talk. So let me just flick through some more pictures for you. Here we go, is another possible configuration. Not one that we're going to talk about because this is the exterior problem. Here's one that is a valid data. Here's an issue with the flow. I'll talk to you why this is an issue, but basically these kinds of configurations expand and don't converge. This is a shrinker, the lemniscate of Bernoulli, and you can arrange your lines. These are not parallel lines, but there's a reason why we consider parallel lines, and it's to prevent things like this from happening. And the actual paper where this appears is called this, and this is a new version of this paper. There was a version of this paper published, well, not published, but the version of this paper put on the internet a few years ago, and we have rewritten half of it. So we're happy. We hope that you will be happy from looking at the talk, and yeah, wish you all the best. Okay. Peace.